Aside from eigenvalues and participation factors, which are based on the harmonic state space model, so they do account for all the harmonic components of the periodic coefficients of the state space model, well, we can also calculate frequency responses. So when I don't know where to start, I always go back to see what is available in the DSA structure. And I remember that I can find some information, some functions, calculation parameters, my previous results of time domain, harmonic domain, all the options and byproducts of the collocation methods, all the options of the time domain simulations, the options that I used for frequency lifting, as well as all my numerical data variables list, the nonlinear state space symbolic representation, the linearized state space symbolic representation, as well as everything related to the LTP matrices and the LTI, which is what results from frequency lifting, so linear time invariant in the form of a harmonic state space system. Here I would like to have frequency responses. So I would like to know from which inputs to which outputs I can calculate a frequency response. This is something that I can find in the variables list. There we are. So again, I know that I have now linearized the system, so I will be working with small signal inputs and small signal outputs. Let's have a look at these. The inputs and the outputs. I would like to have an AC side, of course, single phase, because we are considering a single phase MMC, single phase frequency response from the alternating voltage to the alternating current. This is something that I can do with this part of the code, frequency response calculation. It always starts with an identifier. So here it is an example. I will comment it for later, but I will give a new name for now. This is a single input, single output example, AC side. A variable name is for the inputs, so I would like to start from this alternating voltage. O, a variable name, is for the outputs, and my outputs will be this alternating current. Sign factor, it can be +1 or -1 depending on whether you want a load convention or a generator convention for your frequency response. And then we also have H-in. This is the harmonic channel from which the harmonic disturbance will be considered. You can keep it as 0. And then H-shift is the harmonic shift as a number of times the fundamental frequency, which I will keep to 0 for now, meaning that I'm technically looking for a no-shift frequency response. Also, you have to provide frequency values. This is a vector of frequencies at which the frequency response will be calculated. This is the job done by this FRESP function. I do Control-Enter to run this block of code, and I directly have the result. So, of course, I can observe this plot, and I see that I have many things that are interesting at these frequencies. Not much happens below 10 Hertz. And also I see that I have actually the generator convention, so I can put it in -1. This is just changing the sign convention, and I will also solve it just from 10 Hertz up to this value. I run it again, and now I have more details here. I can also find the results of the frequency response calculations in the DSA structure. You see there is a new substructure that has been included, which is called FRESP, for frequency response. Let's have a look at what is inside. We have the identifier that we used just now. Let's say if I want to do some another calculation, let's see from the direct voltage to the direct current. This is something that I can do. Direct voltage to direct current. Here I will keep the original sign convention and say that this one will be called DC side. Okay, I have it. There it is. If I look again at the available responses, there is the one from the AC side and the one from the DC side. What is super convenient with these very flexible calculations is that you can do even more, like the cross side. For instance, the response from a disturbance on the alternating voltage to the resulting perturbation on the direct current. I can also run this, and there is the result. I see that I have very few dBs, so the magnitude of this particular cross transfer function or cross frequency response is quite low. However, in some systems, these cross transfer functions could be significant, and you might want to analyze them. Checking again what we have in the F response structure. Here we go, we have the three responses that I have calculated. If we look into the first one, we see a few things. We see the input variable, the name of the input variable, the name of the output variable, the sign factor that we used, the input harmonic channel, the harmonic shift, the frequency values over which this has been calculated, and the frequency responses are actually stored inside the last two structures, the harmonic transfer function and the harmonic linearization results. If we look at the harmonic transfer function, well, it is a 14 by 14 matrices over 1000 frequency values. So 1000 frequency values. Why 14 by 14? Those are all the available small signal inputs and available small signal outputs, and each of these are characterized by 7 Fourier coefficients. Hence the reason why the frequency response in the form of the harmonic transfer function is a 14 by 14. We also have the results in the form of harmonic linearization. Here we only have one, and this harmonic linearization is the one that actually corresponds to only the response from this input variable to this output variable. And also for this particular input harmonic channel without harmonic shift, this is exactly what harmonic linearization does. Naturally, you can either record these and save them, save as, or copy figure, and so on. But you can also make your own plots by just saving all the results and getting the frequencies, the responses, the eigenvalues, all the numerical data to make your own figures. So now I think it is a good moment to tell you how to save it. It is very easy. I will save all the calculations. So I save all the time domain waveforms we have, all the harmonic domain spectra, all the options, all the data, all the variables, the nonlinear and linearized symbolic expressions, everything related to time periodic and time invariant representations, as well as my frequency responses, knowing that in LTI I have also all the eigenvalues and that have been calculated. I want to save this. I use a simple function from the function handles, which is save, and I just press enter. For big systems with many data points and very long time domain simulations, well, this saving can take quite some time. However, for this simple system, it took a reasonably short time. Now I know that this DSA has been saved at this particular location. It is saved, it is a DSA, and it's saved on this particular day at that particular time. I can go to my folder, and I see indeed for my MMC with the single phase power stage and circulating current controller, my DSA has been saved here. let's say if I clear all, well, technically I have lost all my calculations, but luckily I have saved my structure, so I can go to my system, MMC, my particular instance, and I import all the data. There we are, it has loaded, and I have again access to all the calculations that I've done earlier. This is quite interesting because at any time, if you have saved your DSA structure, you can go back to the specific data parameters that you've considered. You can check again the options that you used for frequency lifting. You can check the expressions of the nonlinear system that was considered, and so on. So every now and then you can save a DSA structure knowing that it will not be overwritten, simply because if I decide to save it again, well, it is saved, of course, on the same day, but with a little bit of luck, not at the same time. So if I go to the folder, I see that now I have twice the DSA structure saved. To make it even more precise, you can also give a name, like this was presentation of DSAnalysis. And now it is saved with a particular name that I have chosen myself. Alright, so actually I'm not interested in keeping these ones, so I will delete them later. But in any case, this helps you keep track of all your calculations. Let's say from the one that I have just reloaded, if I want to access the time domain waveforms, well, I know they are stored in these results. And I can simply go back to my plot function. I tell it I would like to have the results over the last XP fundamental periods. I don't remember how many fundamental periods that was, so I can go to probably in time domain simulation options. There it is. XP was indeed set to 3. So if I ask Matlab to plot it for these particular variables, it gives me indeed 3 times the fundamental periods.